So, welcome back to this next session on this SWAYAM course meant to enable people who are educators in material science and engineering and allied areas such as perhaps even physics and chemistry educators, other engineering educators who are involved in material science education, materials engineering education in various forms. So, today's lesson plan will be the following. It will again be divided into two parts. One is the pedagogical aspect and the other one is the content aspect. The content aspect will be a continued discussion on polymer science and engineering. The pedagogical aspect, I would like to give you a recap of where we are as of now so that you can position yourself and you can make sense of the next concept I am going to introduce, something called Socratic learning or Socratic circle. It comes from a very ancient tradition of teaching and learning, in fact, and has been practiced around the world and very helpful, in fact, in certainly teaching learning activities. But when you engage students in this kind of an activity, it also helps them deliberate when they are reading, self-teaching, self-learning and so on and so on. So there will be an example of Socratic reading that will be provided in today's lecture, wherein you will find that I won't do much of talking, but there will be some content and it is highlighted. There are very specific parts of the content that is highlighted and which will form the basis of discussion. Okay. So, and through the discussion we will build on where we left off as of the last class. So, the recap as far as the pedagogy is concerned, I hope by now most of you are familiar with the word pedagogy. The other related words that you have learnt are andragogy and heterogogy. So, they are related ideas. In recent times, we discussed some very important concepts that are relevant for somebody who does any kind of a lesson plan and for that matter also comes up with a classroom organization approach. So, what we saw a while ago and which directly connects to this idea of Socratic learning is the following. It is constructivism and we learnt related ideas, constructionism. Constructivist basically establishes a constructionist classroom or a constructionist content is created by somebody who believes in constructivism. It's not actually a belief at all because there is a lot of cognitive science behind this. We understand how the human mind works right now. By and large, certainly as far as information assimilation, accommodation is concerned, and you might recall the theory associated with Jean Piaget, who talks about this way in which the mind, which is essentially an information absorption and processing platform, it takes in new information based on pre-existing schemas and then the schema evolves. So, there is a pre-existing schema, the new information comes in, it is assimilated and then when it is exercised, it becomes accommodated. And this is really what we should help our students with. It is essential for them to sort of, number one, understand that they can build on lessons from where they come. Number two, for them to see a matching point, a meeting point between where they come from and what we are offering them in a classroom setting so that they have a context for learning. So, constructivism, and this is a very critical term especially for appreciating Socratic learning. So, constructivism is an approach towards nature of knowledge and I introduced this idea of ontology. And I told that this is really not something that is specific to education research. It's also used as a concept in, let us say, philosophy, information science, computer science and allied areas. So, it is a very profound philosophical concept. It enables us to see how knowledge emerges or the nature of knowledge itself. And that's really one of the deepest things that we can actually tell to our students. One of the best things we can bring to the classroom setting. So, constructivism is an approach towards nature of knowledge that in that it is an ontological approach, and I would like to remind you that the knowledge maps that we have seen in this class, including let's say the tree diagrams or the spider diagrams or the concept maps, mind maps that we have seen in this particular classroom are all example of ontological maps because they are visual representations of how knowledge has come about, the nature of knowledge in a particular domain. So, it comes off by and large today, as of now, comes off the work of a developmental psychologist called Jean Piaget. Really, it is not that he was the first person to construe this way of learning and this way of thinking about knowledge. It has been around for a really long time, certainly within teaching traditions and also within philosophical traditions. So the emphasis is on understanding how human beings make sense of the world. So this is very critical. I mean, whatever we teach, it should be in the context of the world that our students inhabit, and that is rather important. So from constructivism comes this idea of constructionism. So for instance, I am a constructionist in many ways, in the sense that I ask students to make tree diagrams, knowledge maps, spider diagrams, or ask themselves where they come from, what they think about a certain question, and try to build on it. You don't have to refute it entirely, but build on it by using, let us say, a scaffolding technique. And scaffolding technique is also, in a very fundamental sense, a constructionist approach. So this is key. In the constructionist learning, learners understand by creating mental models that are discovered by them through their experience and built on their pre-existing knowledge. This is very key. And I have told you the importance of this kind of approach, this kind of intellectual formation even in the lives of MS PhD students, because MS PhD students are expected to discover, to explore, and unless and until there is a real appreciation of how they would go about doing this, they might not necessarily get the best out of the course even. So it is very essential for us to sort of, as a consequence, set up a platform wherein they are open to self-discovery, build on already existing knowledge that they have, and see how the pre-existing knowledge and the new knowledge comes together to form an information landscape that is relevant for them. And in this context, we have talked about connectivism. Connectivism is very essential today more than ever before. I tend to connect to my students, for instance, through social media quite extensively. Now, this is something that wouldn't have happened if I was born, let us say, even 30 years ago, or the students were born even 30 years ago, if this was a different generational setting. But today, we are capable of using sort of the digital connect in order to create platforms. For instance, provide reading material even before they come to class, or provide a flipped classroom setting which becomes a scaffold material essentially for all practical purposes. Providing some organization for the content that you cover in the class, so that you don't spend a lot of time on the board. The student already knows a little bit of the schema and you fill the gaps. So there are very dynamical approaches to using technology in this digital age, and that connects with this constructivist approach, and that is called connectivism. And of course, you can use this in the context of a wide variety of learning. And something rather interesting that I wanted to just mention, not that it is relevant to this course, is that this is how machine learning actually operates. It is through constructivism and connectionism. Machine learning actually operates this way. If you have seen the robot Sophia, she is constantly learning while you ask her questions. And how does she do that? She actually uses a combination of connectivism and constructionism. It is that kind of an ontological map that is built into the software that allows learning by a machine, and that's not very different in some sense from the way we learn. The fundamental difference, as far as I can say, is the emotional component. In the case of the human beings, you take the emotional components out, you would think learning improves. It doesn't. There's a lot of evidence of that as well. So that seems to be the difference between machine learning and the way in which AI works and the way in which human minds work, and that's an area of research by itself, something that I wouldn't want to go in much. But with this as the backdrop, and also if you recall schema essentially represents a pattern of thought or behavior that organizes or categorizes information and identifies the relationships between them. So you have information, you categorize information, and you see relationships between information. You see how this piece of information, when transformed, gives rise to this piece of information. How this piece of information is connected to this, and so on. So these schemas exist in everybody's mind. And these schemas evolve over the course of a human being's life. And that is precisely the Piaget's cognitive development model that I told you about last time. And by and large, college and university educators don't have to worry about the top three parts, because that has to do with primarily children who are developing, whose mental processes are developing. They tend to be very physical in their learning. They may not understand symbolic thinking completely, but they would have started thinking about it beyond a certain age. And they would be able to at least label, discuss, describe relationships between objects in some way, but they may not be able to hypothesize. the ability to hypothesize, the ability to be very theoretical, for instance, is an adult characteristic. It is a characteristic that is typically seen in adults. There are exceptions, of course. There will always be people who are precocious, but by and large, the use of abstract logic and reasoning is something that college students can do. They were not able to do it when they were younger. So the kind of questions we ask them as a consequence should represent a little bit of each one of them. And this in some sense maps out to Bloom's taxonomy as well. Okay. So let us come to today's idea. And today's idea is something that comes from the Greek tradition. In fact, it's a tradition that is very, very old, around 2,300 years old now. So it comes from the way in which Socrates, the Greek philosopher, ran his school, his teaching learning center for all practical purposes. And it is recorded in the writings of his students. So he did not leave a lot of writing, but his students left quite a bit of writing about how teaching learning operated in those schools. And the method is actually called the Socratic Method, but in some literature you will find that it's called the Myonautics Method. In some other literature it is called the Elenctic Method, and in some other places it is called Socratic Debate Method, but they are all exactly the same. So based on the book you read, the textbook that you read on education methods, you will find that these different words might be used, but they are all exactly the same. So that is the first thing that I wanted to mention. So what is it? It is a form of cooperative learning through argumentative dialogues. Now this need not be necessarily a debate, it has to be a dialogue. Okay? So wherein the student doesn't necessarily feel that he has to win the argument or she has to win the argument. That's not the point of this discussion or this dialogue at all. The point of this dialogue is to sort of be open and say that this is what I understand, but I am open to the possibility of other ways of understanding, other ways of thinking. Okay. So the key here is to stimulate critical and clear thinking through questions that draw out ideas. Now this, it turns out, Socrates was an expert in. He would ask just the right set of questions in order to lead to the next question, to the next question. And in some sense, almost 2,400 years ago, this man was actually using the constructivist approach of building knowledge. So that's a rather remarkable thing if you think about it, because people in various educational systems have actually thought about how human beings learn. And it is now, of course, backed by science, but people knew it, maybe even experientially, the way in which Socrates knew. So this is the key word here. It is to stimulate, critical and clear thinking. Now this, by the way, is rare. It is not as common as you would think. Okay? So it is rather rare. That draws out ideas and enable questioning of assumptions. So for instance, a student may say something and it might be based on an assumption. Now you could do two things. One is you could say, oh, that is wrong. The second thing you could actually say is, why do you think this? And then you might realize that there is an assumption wherein you could actually provide the data and then you could evaluate that assumption. Alright. So it is important as a consequence to not just stick to one level of evaluation, especially in the Socratic method. It is very important for you to ask, okay, what do you think about this? And then you evaluate the thought of the student and then say, okay, why do you think this? And if there is an assumption that needs to be questioned, for instance, you question it. If you can provide data for the same, you provide it. You could use the connectionist approach for that. You could ask them to look for data on Google Images or Google Scholar and so on and question the assumption that might be underlying this. Okay. So it is a dialectical method. That means it's a dialogue driven method. So the emphasis is not on monologue, the emphasis is on dialogue, through which a combination of an iteration of thesis proposition. By the way, this is where the word thesis comes from. So what you do is you basically create a position statement. So that is the thesis position. So the student or the teacher makes a thesis and says, we'll have to evaluate whether it is reasonable or not. So we'll have to provide discussions around it, provide evidence, and see if the thesis stands the test of iterations. So iteratively, you come about the solution to the problem. So there is thesis proposition, debate, questioning of the assumption, and revisit the position. So if, let us say, the original hypothesis was not good enough, you revisit. So there is a hypothesis, you test the grounds of the hypothesis. If the grounds are incorrect, correct it, re-hypothesize till you come to a statement that seems to be reasonable and that is driven by data, that is driven by reason, that stands the test of this iteration. By and large, if you think about it, this is where the scientific method also comes from. What is the scientific method? It starts with a hypothesis. You need to experiment it out, test it out, evaluate the position, revisit the hypothesis, and go through this loop again and again. So this is remarkably similar to the scientific method. So the big difference between the Socratic method and, let us say, the Bacon scientific method is that Bacon emphasizes empirical investigation. He says, look at the data. Alright, while here it is not explicitly mentioned because it's a general teaching tool. Okay? But by and large, this establishes the foundation for scientific thinking. This process quite naturally helps in achieving better hypotheses and results in elimination of poorer choices. It makes a lot of sense, isn't it? The questions are usually formulated to test the logic underlying the thesis proposed. So this is an important thing, It is not sufficient to just say this is the method I will use. It's very important to design a set of questions. So in some sense, it is like design of evaluation. Earlier I had talked about the design of evaluation, but here you're evaluating the hypothesis. So you design your questions to evaluate the hypothesis and re-evaluate the hypothesis and so on. And that is an art that you can certainly teach your students. And it's tremendously helpful for learning. So what is the Socratic seminar or the Socratic circle? It's a pedagogical approach based on the method that I have described in the past, just recently, the Socratic method. It uses the idea of discourse to examine a text through questions and answers. So sometimes what happens is we may not be able to immediately do the experiment and test it out. More often than not, that is the case. Alright. So what do? You can provide a text then with some data, some content, some written material, etc. And you can use that text as a basis for argumentation, for discussion, for discourse. And I will show an example of that in the context of a topic, let us say polymer crystallinity today. So it's a cooperative activity and there need not be a debate. It could be a discussion, it could be discourse, it could be argumentation. It need not necessarily be a debate wherein both sides feel that they have to win or something like that. There's absolutely no reason for that. Now a tool that is rather modern, that has come off this kind of a tradition, is called the Harkness method or the Harkness discussion method, and this emphasizes the importance of providing a space like this. So you get the students to sit in a configuration that allows, there's an error here, that allows discussion of ideas in an encouraging open-minded setup. So typically the tables will look like this, or they could be round tables or oval tables. So you get students to sit so that they see one another and they can actually discuss with one another. And so you can use the Socratic method in an ambience, something like this, and this is called the Harkness table or the Harkness method or the Harkness discussion method. So you can run a Socrates seminar, for instance, or a Socrates circle by using this Harkness table method. Alright. So there are some questions to ponder which I will leave for the next session because I will connect it with the recap part that I do in the next session. Okay. So we will come to the content part and we will try to use some of these techniques that I have mentioned here. So I have taken content from Wikipedia, which is covered under Creative Commons license, and I want to use this text which has some specific pointers or questions, okay, to point students to some specific text. So they may not have the time to go through the whole text in the context of the class. They could do that later, but during the class what I am going to do is I have a set of questions for them, some activities which is meant to be Socratic in nature, so that they learn about polymer crystallinity and the relevance of it as far as some applications are concerned. So that is going to be our approach as of now. So before we go there, can we spend about, let's say, 5 minutes recapping what we did in the last session as far as polymers is concerned? Do you have your notes with you? If you don't, you can recall, you can use your memory and tell me a little bit. So let us do a recap as far as polymers are concerned. So what are some of the things that you learned? So in order to make it a little easy, what you can do is maybe you can sit together and make a tree diagram of all the things that we learnt last class with the connects, okay, between the tree diagram, and then we'll reproduce a tree diagram on board. Shall we do that? Because that way the sum total of memories is actually made available in a single tree diagram. That might be a little easy. Very good. Block copper, block polymer, block copolymer, then random polymer, branched polymer, linear polymer. Then we also discussed tacticity, if you remember. And remember that I left you with one homework problem, which was the cis-trans isomerism. So at the end of this tree diagram, I'll ask you to sort of draw on board about cis-trans isomerism, and we will use that as a starting point. Okay. Graft, G-R-A-F-T, graft. We discussed glass transition also, supercooling, Hausman paradox, if you remember. That is the least temperature at which you can ensure that it continues to be liquid. So we discussed the Hausman paradox. How did we discuss this? Using ST diagrams, entropy temperature diagrams. Yeah, correct. Okay, monomer versus mer. So monomer is not same as mer. We learned that also, isn't it? Yeah, for instance, you could actually have mer1, mer2 that combines together to give rise to a monomer, and that repeats. Where do you have molecular weight? So you have two types of molecular weights. So do you want to show it like this, or do you want to show it in the form of branches? Because this is a tree diagram. So we looked at Mn bar and Mw bar. And this Mn bar is related to some properties, and Mw bar is related to some other properties. So can you write out one or two properties that Mn bar is related to? Some properties, yeah, mechanical properties in general tend to correlate quite well with Mn bar. Transport properties on the other hand, including viscosity, the rheological properties, etc. tend to, yes, so the rheological properties, viscosity, etc. In fact, viscosity is also a transport property, right? So that makes sense. And then where did you write glass transition? Okay. So using glass transition, we also explained why some plastics are hard at room temperature and some, yes, very good. So not just thermoplastic, why is it that some are hard and some are soft, right? So for instance, the eraser, it's a rubber, you can very quickly bend it and so on. Yes, so the glass transition is much below room temperature, and as the glass transition gets higher and higher and closer to the room temperature, it becomes less and less pliable, right? So it tells you a little bit about flexibility, the elastic properties, right? Flexibility and elastic properties, or pliability you can call it. So TG can be correlated with each of those things. Right? And then the more crystalline an object is, suppose you have crystallinity, what would happen? Did we discuss about crystallinity? I did tell you some story about DNA crystallization being important for determining the structure of DNA, and the fact that one of my friends spent 3.5 years trying to just crystallize one protein. So all of you are lucky. You don't have to do that. So because it took 3.5 years for her to figure that out. But that's evidence that polymers do not crystallize easily, isn't it? So, so what shall we write? So there you can have atactic, isotactic, symbiotic, right? So does tacticity correlate with crystallinity? So if you have an isotactic system, it's easier to crystallize. If you have an atactic system, that is not easy to crystallize. So why don't you write that down? And then crystallinity, it's never 100% crystal. So typically 35 to 50% is about as good as it gets when it comes to plastics. So one of the questions I asked you was, I have two polymers with the same composition, how different can they be? And they can be very, very different, right? So does processing determine how these polymers come about, the degree of crystallinity? So maybe somewhere you should add that into the knowledge tree. And maybe you can redraw that knowledge tree, because it's not, right? For instance, you could do monomer, and mer could come under that, wherein you could actually have mer1, mer2, okay, or block polymer. So why don't you redraw this and make the connectivities more explicit? And also there are some connections between this and this, this and this, and so on. So let us look at that. So this is a first level connect, but that's not sufficient. There could be a second level connect also. So why don't you think about it? So just to be clear, at the moment I am using very little of Socratic method. I am just getting them to recall lessons that they have learned from last time. So they are just making ontological maps as of now, okay. Primarily tree diagrams. Did you do an example last class for calculating Mn bar and Mw bar? You did an example also. And have you written tacticity somewhere? Tacticity is there. So syndiotactic, isotactic and atactic. Yeah. So another thing that I did mention to you are the various techniques that you could use, right? So TG can be determined by using differential scanning calorimetry. So I have put it up there to enable your tree diagram. Molecular weights can be determined by using colligative and diffusive properties. Structure uses NMR and X-ray scattering. Crystallinity typically is densitometry, and it uses Archimedes principle. Degree of crystallinity comes from Sachs, so something called small angle X-ray scattering, and there can also be small angle neutron scattering, so that is called SANS, alright, and oftentimes these techniques are used in conjunction with wide angle X-ray scattering to understand meso and nano scale. So meso is between nano and micro scale. And is there any correlation between molecular weight and melting point or glass transition that we saw? Any correlation between glass transition temperature or melting point and the weight of the polymer that we saw? We saw this, you see. This was the last thing that I showed you last class. So it increases and almost saturates. You remember? So that should also be there in your tree diagram. So you learnt a lot in the last class, in fact, you know. So that should also be there in tree diagram. And these characterization techniques too, alright. So you please populate those characterization techniques. For instance, if I wanted to do the glass transition temperature, I wanted to determine glass transition temperature of a polymer, I would use DSC, differential scanning calorimetry. So it's a calorimetric tool. Why so? Because there is an enthalpy associated with crystallization, isn't it? And molecular weight, it's this combination of colligative and diffuse properties. What is colligative property? Yes, it doesn't depend on the chemical property, it only depends on the concentration, yeah, on the number of one species in another, okay. So make sure that you have some mention of this, DSC, colligative and diffusive properties, NMR and scattering, densitometry, Sachs and SANS. So please mention that somewhere, because I told you, we have not discussed these techniques in great detail, but I told you that these are the techniques that you would use if you wanted to determine this property. Alright. So we have not discussed these techniques in detail. Good for you to actually represent it in your tree diagram, and if you are interested in learning more, you can read about those things. This also needs to be represented, TG, TM versus molecular weight. Did you represent this thing, Malik? These techniques, DSC, colligative, diffusive, NMR, X-ray scattering, Sachs, SANS. And did you incorporate this in your tree diagram? This, yeah, TM and TG both increase and eventually almost saturate as a function of gram molecular mass. And there are these different kinds of polymers. We did discuss linear polymers. You remember? Linear, branched, grafted. There is another kind of polymer. So you can have 2D branched cross-linked polymers. So do you have it? And this is an interesting thing, you can put that into your tree diagram. See, vulcanization of rubber, for instance, is actually an example of going from relatively linear chains to cross-linked polymeric structure. So you have otherwise linear chains that can flow past one another, but now what you do is you stitch them together through cross-linking, and hence they do not flow that easily, alright. So do you think this will affect the glass transition temperature? Absolutely, it would affect the glass transition temperature. So those are called cross-linked polymers, and a good example of this vulcanization of rubber. You know, vehicle tires would not be possible without vulcanization of rubber, okay. And then network polymers. Now this is interesting, I did not mention this explicitly last class. You need to have trifunctional MER units. So what are trifunctional MER units? You have one functional group, 2, 3. Tri, what does it indicate? 3. So there is possibility, so yes, so when they actually polymerize, there is real possibility of having a 3-dimensional network. And so that is why network polymers are those that usually have trifunctional MER units. having 3 active covalent bonds. So, each one of them is capable of forming 3 active covalent bonds, and as a consequence a network forms. Okay. So, it becomes a network system. So, these were some cartoons I showed. Linear, you can see there is absolutely no branching. There is branching here, and a special case of branching would be the graft polymer that you have seen in the past, and then network polymer. And this is the kind of stuff that would require a trifunctional mer. Okay. So, can you write that down? Can that be populated inside the knowledge tree that you are making, the tree diagram? So, did you talk about tacticity in your tree diagram? Okay. And what is the degree of crystallinity typically in the most crystalline polymers? Between 35 to 50%. You know, if you get about 50%, you are very lucky. Alright. And then let me see. Okay. So, I think that more or less covers it. So, can you show me your tree diagram now? Polymer. Okay. Merge, block, random, graft. Actually, that is not entirely true because remember, mer is the fundamental unit. So, you could have mer1, mer2 and that could actually become the monomer, or you could have mer1, mer1, mer2, mer2, you know, that could result in, so, or you could have monomer 1, monomer 1, monomer 1. So, you have A, B, 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 and then you would actually have A3, B3 repeated to give rise to a block copolymer and so on. So, it is independent of mer. Mer is a more fundamental unit than monomer. That is really what I wanted to say. Yes. So, you could actually make the links like this, you know, from based on how the monomer repetition. So, the transformation that you are talking about here would be repetition. So, here based on the repeat unit, you could either have this, this or this. Yeah? And then molecular weight, of course, you can describe it using number averaged. So, you have the formula for that, right? And then, or weight averaged, you have the formula for that, and typically mechanical properties correlate quite well with number averaged molecular weight, and the transport properties correlate quite well with the weight averaged molecular mass. That includes things like diffusion coefficients and so on. And then isomerism, stereo geometrical isomerism. Geometrical isomerism, cis trans we have not seen yet, but then the stereo isomerism, iso, syndeo and atactic. And there is a correlation between this and crystallinity. What is that? So, if you have atactic, you have poor crystallinity, right? While if you have isotacticity, you will have high crystallinity. Okay. And then, okay, high crystallinity. So, this TG, this TG is related to molecular weight, isn't it? So, higher the molecular weight, typically, higher is the TG. So, higher molecular weight, higher TG. That is this relationship here. And in order to make something very crystalline, do you have to do slow cooling or rapid cooling? Slow cooling. So, there is a process connect. So, this comes from slow cooling, you know. So, the crystallinity increases if you do slow cooling. And then TG and TM, there is a lower limit to the degree of supercooling you could do. You have seen supercooled liquid, and the question was glasses versus amorphous solids. You remember? So, glasses are those that usually have glass transition temperature. All amorphous solids need not show the glass transition temperature. So, if the moment you see a TG and there is a DSC signature, the moment you have these two, it is usually a glass. So, you have a glassy polymer. The moment you see a TG, and polymers typically will give you a TG, but in the world of inorganic solids, you could actually have a system that is amorphous but not glassy. That does not show this glass transition temperature. How did you determine whether or not it was a glass? What was the graph that we used? Specific volume as a function of temperature. So, this came from V versus T curve, correct? This came from V versus T curve. And then we evaluated this TG versus TM on the basis of the Kauzmann paradox. You understand that. And the Kauzmann paradox was argued by using S versus T curve based on the slopes associated with them, right? Now, when you have crystallization, the slope is abrupt. In the case of the specific volume versus temperature, you have an abrupt change in the slope. Okay, but in the case of a glass, what happens? You have a gradual change in the slope, so you will have to do extrapolations in order to get the glass transition temperature. So crystallinity, in order to determine it, you will have to do typically densitometry. So you use the Archimedes principle. So that is densitometry, correct? Now what are the other things? Now if I wanted to study any of these kinds of properties associated with the structure of the polymer, what would I do? I could use NMR, isn't it? So this could be studied by using NMR, correct? Now if I want to study the molecular weight, how would I study that? Colligative properties. So measurement will be based on colligative properties or transport properties, that is diffusive properties, correct? So that it comes to the molecular weight. An example of cross-linked polymer is vulcanized rubber, very good. What else have we missed here? Okay, if you wanted to understand the degree of crystallinity, what would you do? Measure. So to measure it, you could do small angle X-ray scattering or small angle neutron scattering, or you could do wide angle scattering. So that is another thing that we saw. Of course, to study TIJU, you could do DAC, TGA. What else is missing here? So let us look at the characterization part, because that is rather important too. So glass transition temperature, DAC, you have written that, right? Molecular weight, colligative and diffusive, you have written that, alright? NMR and X-ray scattering for molecular structure, that includes study of isomerism, right? And then polymer crystallinity is determined using densitometry most frequently. Degree of crystallinity, sacs, sands, and so on and so on. Okay. And these are new terms for you. Mesoscale. Mesoscale is actually the scale between nano and microscale. Okay. And then what was the correlation between TG and molecular weight? Did you write that down? It increases and saturates. See, TG and molecular weight. So TG, higher the molecular weight, higher is the TG. So it looks a little funny, but as homework, can you make a nicer tree diagram and give it? So we'll show it. At the moment, I'll show you a rough version of the tree diagram that was made by the class with some props from me. So it looks very rough at the moment, but they will make a neater version of this, and that will be part of their homework. So you can see that they have connected the idea of monomer to the idea of mer. Then they understand that molecular weight can be categorized into number averaged and weight averaged. They also understand that this can be measured by using colligative or diffuse properties, and they also understand that for the same chemical formula you could have isomerism, that is either stereo or geometric, alright, and there are ways to actually evaluate that using NMR. They understand that there is a correlation between molecular weight and TG in turn can be determined by using DSC, TGA and so on, primarily DSC, and then that the degree of crystallinity can be studied using densitometry, and the fact that the degree of densitometry is here. To achieve crystallinity, you need slow cooling. They also understand the Kauzmann paradox, which actually establishes a lower limit for the degree of supercooling you could achieve. They have given a few examples. For example, for cross-linked polymers, they have given an example of vulcanization of rubber and so on. So seems like the last two classes they learned quite a bit, and they have represented it here. So Varada, can you make a cleaner version of this diagram and send it to me, and we can flash it next time in the class. So seems like you learned quite a bit. Good, very good. So now let us reconvene. You can go back, okay, and we will start a reading process, a textual reading process. So we'll dig a little bit more into this idea of crystallinity, alright, and let us start with a question, and that's really how it becomes Socratic. Let us start with a question, okay. So what is crystallinity? Crystallinity is the degree of, yes, so it gives you some idea regarding the long range order. Do you think it will influence properties of the polymer at all? Of course. Now what are the kind of properties that you think crystallinity will impact? So let me write that down. So I am going to change the degree of crystallinity. Alright. So crystallinity impacts what? Okay, so density is certainly one variable. The more crystalline it is, the more dense it is likely to be. So as crystallinity increases, the density also increases. Very good. Next, strength. Very good. So now let me say that I am dealing with linear chains. Okay, so that's equivalent to saying that I am actually having a bunch of these chains. Okay, so what I am going to do is, so these are the polymeric molecules, okay, and I am aligning them along one another. So it's aligned like this, okay. So now what I am going to do is I am going to do a tensile stress test. I am going to actually pull it in this direction, and in another experiment I am going to pull it in this direction. Do you think the strengths will be different? Of course. So the strength, so based on the direction of crystallinity, so the direction of crystallinity, let me just check. I made a mistake here. Determines anisotropy. So anisotropy simply means difference in properties in different directions. Anisotropy in modulus. Okay, so strength. Can you give me one more example wherein this is likely to be different? Okay, I'll give you a small problem to think about. I am going to ask you the same question but in a slightly different way. I want you to come up with a product, okay, made up of polymers that has the same composition but different colors. Is it possible? Is it not possible? So the composition is the same, okay, the composition is the same, but I want different colors. Is it allowed? Disallowed? If so, how would I do it? So discuss with one another, please. Yeah. So what about different colors? How about making lenses, polymeric lenses, by playing with this parameter crystallinity? You understand the question? So the teachers observing this lecture could note that I am trying to give leading questions and I am going to get students to think about the relevance of the content that they are learning. And these leading questions are questions that might require them to think at various levels in the Bloom's taxonomy. But most importantly, it is very essential for you to sort of make sure that students build on the knowledge set that they already have. For instance, they already seem to understand that crystallinity has a bearing on the properties, and they were able to come up with reasonable arguments about it. Now you put them in a new context so that they assimilate new information and that information gets accommodated. That's another way of thinking about it. So Socratic method is actually helpful in getting students to build on already existing information. So this is the information on the board is what came out of them, and then the question is what came out of me, and the question is the leading question, and that is the Socratic method. Okay. Yes, it is possible. It's possible. Okay, so how is it possible?
Crystallinity is more actually the scattering of light depends on the crystallinity. If it is crystal, the scattering will be less.
So let us think about this a little carefully, but complete your sentence, please. Yeah.
I am thinking that if it is crystalline, then the scattering will be less.
So let us think about it in rather simple terms. Yeah. So what are the constituents of visible light? The VIBGYOR, right? So VIBGYOR. So can you look up use your data and find out what the visible light looks like? What are the wavelengths? Okay, that's 400 to 700. Makes sense, right? So 400 to 700 is, now I have, let us say, a thin sheet of plastic and I look through it, it looks, let us say, red in color. What does that tell me about the light? So I am shining white light and from this side I see red. So what is the transmitted light? Red. Correct? The transmitted light should be red. On the other hand, I actually see some green on this side. So white light is falling here. Here I see green. I see green when I look up the plastic. So what is the transmitted light? Green. So another way of asking this question as a consequence is the following. If I keep the composition constant, what are the parameters I can change associated with this film of the polymer that will allow me to change the transmittance spectrum? That's another way of thinking about this question. There are various ways of thinking about this question, but this is one way of thinking about the question. Changing the transmittance spectrum. Alright, do you think that the transmittance spectrum will be dependent on the crystallinity? It has to be, because the transmittance spectrum is determined by the portion of the light that is not absorbed, okay, and crystallinity does influence the kind of bonding that is there in the system. But to be honest, transmittance spectrum cannot be entirely engineered just by playing with crystallinity. You will also have to play with thickness. You will also have to play with thickness. So I just gave you two hints. So if I wanted to make a layer of plastic and I wanted to make it colored, there are some parameters I could play with. One is thickness and the other one is the degree of crystallinity. Now the degree of crystallinity, if I vary it, do you think I can make something like a Polaroid? You know what Polaroid is? You have light that is unpolarized, you get out light that is polarized. Is it possible? Why do you think it is possible? You are right. So why don't you discuss this with one another? So you have studied it somewhere in your +2 physics or so, that light that is unpolarized is something wherein the electric fields are not necessarily in a single direction. They basically vary randomly. So it basically has a combination of electric fields that are oriented in different directions. Polarized light, on the other hand, will have electric field that is highly oriented in one specific direction. So what does this tell you? Suppose I actually had a polymeric film, okay. Can I use this polymeric film to make a Polaroid? You know what Polaroids are, right? Polaroid cameras, for instance, they use polarized light. So light to begin with is unpolarized, it is polarized and then you use it for getting your pictures. So those polymer films, okay, can I make them by using a polymer? Can I make them progressively Polaroid? That means a better and better Polaroid by controlling the degree of crystallization it has. That's the question. If so, why? If not so, why? Yes, what are your answers? Yes, no? Yes. You think that we can use polymers in order to make a Polaroid film? You think yes. What do you think? Yeah, you are absolutely correct. There is a way to make, in fact the Polaroid films that are used in cameras, they actually are made up of polymers. And now that you know that you are essentially playing with crystallinity, so you align it. So the orientation or the crystalline axis is actually the optical axis for this polymer, okay. So what happens is the crystallization direction, the direction associated with it determines the optic axis. That means that is the axis along which light would go. In any other direction the light would actually get diffracted. So if you shine light that had if you shine light that had a component that is in the direction of the optical axis, vibration in the direction of the optical axis, and some vibrations that are not in the direction of the optical axis, they would get refracted differently. So you would have two separate refractive indices. You would not have one refractive index, you would have two refractive indices to report. One in the direction of the axis and the other one perpendicular to the direction of the axis. So you would have two completely different refractive indices. So based on the polarization of light. Okay, so that's rather interesting, isn't it? So you can get polarized light from unpolarized light by using a Polaroid, and the Polaroids, most of them are actually, a large number of them that are actually sold now are made up of polymeric films. How can I manufacture them? Now that we know that we need crystallinity, we need an axis of crystallization, we need a direction of crystallization and so on. How would I make it? Can you discuss? Why don't you discuss with one another? That's right, that is one way. Yes, you can actually, increasingly people are thinking about solvent evaporation technique, very controlled solvent evaporation technique with some thermal gradients. Another approach that is used is actually called the extrusion technique, polymer extrusion technique, that we just pull out something to do with that, or injection molding also. So this is a technique called injection molding. The direction in which you are injecting will be the direction in which there is stress. Now you see, in this particular case, alright, you are feeding your polymer here, P is polymer, and you are also applying pressure. You are heating it up and it is going through a nozzle. Did you see that? So in which direction are you applying stress? In the perpendicular direction. So that is the direction in which you can actually expect alignment of the molecules. Okay. So on the other hand, as it is melting, if I am actually applying stress in one direction, I am applying shear in one direction. That is the direction in which I can actually expect crystallinity. Now, would I work with an isotactic system or a syndiotactic or an atactic system for getting this kind of polymer? Iso. So if I do not work with isotactic polymers, it's very difficult to make a Polaroid. So I need to use an isotactic polymer. I need to use something that is workable, castable, and which is going to be either injection molded or extruded in a certain manner such that there is stress in the direction, in a certain direction, so that there is crystallinity in that particular direction, so that there is an optical axis that emerges as a consequence. Alright, and when this is done along with suitable thicknesses and so on, you actually have a Polaroid. When this is done, you have a Polaroid. When you have a thick enough sample, you will have very, very good polarized light, fairly good polarized light. Alright, and also when you vary the thickness of the film, let us say that you have thickness of the film that is of the order of the visible light, such that certain wavelengths undergo destructive interference. Okay, so you have this thin film. So you have a thin film. Alright, light is incident, light reflects back, light is incident, light reflects back, which means here it is undergoing constructive interference or destructive interference. So wavelengths that undergo destructive interference here will be the wavelengths you don't see, because they are destructively interfering, right? Now clearly this thickness D determines which wavelengths will undergo destructive interference here and which wavelengths will not undergo destructive interference here. So I can play with the thickness and get different colors. So my question was, can I get different colors? The answer is yes, I can get different colors. So it is not just playing with crystallinity, but playing with thickness of the film. And in this particular case, you can show that the thickness of the film should be roughly lambda by 4 for destructive interference. Makes sense, isn't it? You all remember this? So the thickness of a thin film should be roughly lambda by 4 for it to actually have destructive interference there, right? So I can certainly get various colors. So this will look differently on this side, this will look differently, correct? So I will get different colors. Can I make lenses out of it? Absolutely yes. So here I am making a filter. So it's a in fact very high resolution filters can be made by using polymers. A lot of optical lenses that are being sold are not necessarily glassy systems. They are actually polymeric systems, and this is how they are made. You control their thicknesses, or you overlay one on top of another. You make a sandwich structure, you overlay one on top of another. So if you look at it and look at it under the optical microscope, you will see that there are layers. And that is how it basically becomes a high resolution color filter. So polymeric filters can be made that way. They can be made to be colored that way. You can make lenses, including basically filtering lenses. So I can basically make filters out of it, wavelength selective filters out of it. And similarly, I can also make a Polaroid lens by having an optical axis, by making sure that light that is unpolarized to begin with, only those electric field components that lie along this particular axis, they go through axis, the others basically get scattered out. So you basically get polarized light. Okay. You understand? So very fascinating, isn't it? So you can use extrusion approaches or melt shear approaches, or even increasingly solvent vaporization techniques people are using nowadays. But there the big challenge is actually introducing a stress. but there are approaches that people are exploring there to introduce stress as well in order to make each of these. So you can actually make a product by just playing with this. So you have gotten some ideas to make a product, an optical lens, a wavelength selective lens, colored lenses, okay, and you could actually use a combination of these in sandwich configurations, and you could make a Polaroid, okay. All of these basically become possible. So if I have sunlight, I want to filter out sunlight, I could actually come up with a solution based on polymers using some of the ideas that we have discussed in this class. So very good. So this is the injection molding technique. So you have the nozzle, you are applying pressure, this is the charge is the new polymer that you are feeding into the extruder, and in this direction you can actually expect the polymer to flow. So because it flows in this direction, you expect molecular alignment in that direction. Here is where it will likely lose that alignment. So if you can actually make sure that when you are casting it, you don't lose alignment, you get the full benefit of the pressure, your design would be ideal for ensuring crystallinity. This is not a design for just crystallinity, this is a design for casting. But the design for crystallinity would be such that the pressure would basically be propagating through all the way till the final cast, you understand, and that is very, very important. So you can see you have sent the charge in and it has basically resulted in these parts. But remember that when you send it through this, you might lose alignment. So when you are designing for optics, you should design a process, an extrusion process or an injection process or a melt based process or a solvent based process, such that the stress propagation or the stress is actually there in the molecules as they set. If you don't ensure that, you cannot ensure any of these things. It is just not possible. So it's a very specialty area in polymers to make optical lenses and casting optical lenses, the specialty area because of this reason. But by using these ideas, you can now think about this problem. You can now start thinking about this problem, okay. So interesting, isn't it? Good. Alright, so let's go back to this. So one of the first questions that I asked was based on a fact. So I gave you a fact, crystallization occurs much more easily in isotactic systems than atactic systems, and I asked you the question, draw cartoons and propose a reason for this. I suppose you already can understand this, right? So maybe that exercise we can skip. The next one is very important. Nucleation starts with small nanometer scaled areas, whereas a result of heat motion wherein some chains are aligned in parallel. It's bad English, but anyhow, the bottom line is nucleation, they say, is a region wherein these polymers are aligned with respect to one another. What is the usual scale associated with it? Nanometers. What is nanometer? 10 to the power of minus 9 nanometers. So here is a statement, okay, and then there is another statement. It is strongly affected by impurities, dyes, but remember you can add dyes to change the color. So that's another way in which you can change the color. So you can use dyes or pigments here. So the answer is yes. So you can play with thickness, or you can play with dyes, pigments, or you can also play with thickness, dyes, and also to some extent, not much, to the degree of crystallinity. In fact, crystallinity sometimes, in the case of some polymers, is so dramatic in effect. Based on the crystallinity, you can go from a transparent system to an opaque system. The same composition, you just play with the crystallinity, you can actually completely change the kind of polymer that is. So crystallinity as a consequence is a pretty powerful handle, but the most frequently used handles are thicknesses, dyes and pigments. And this is interesting, nucleation is strongly affected by impurities, some secondary phases that might be there in the polymer melt, dyes, plasticizers, fillers and other additives. So can you look up the definition of plasticizers? This is interesting. Plasticizer, what do they mean? And also think about why other phases in the polymer melt would influence the nucleation process. So what are plasticizers? Do they increase TG, decrease TG? They promote plasticity, that promotes brittleness, okay. Reduce brittleness, okay. Increasing flexibility. So is TG going to be decreased or increased? Decreased. So plasticizers usually? Yes. So why do you think that is the case? So I have these polymeric chains and I am introducing these plasticizers. So some of the most commonly used plasticizers, let us say in PVC for instance. So PVC typically is brittle. So but in order to make it a little bit more flexible, people typically add some phthalate plasticizers. So they are called phthalate, PHTHALATE, phthalate plasticizers. So why do you think that phthalate plasticizers help in making this PVC more flexible? So what is happening to TG? What is happening to TG? The TG is decreasing. So the flexibility is increasing. That makes sense, right? So why do you think that the TG is decreasing? Correct. So you have these molecules, they are typically bonded to one another via van der Waals interactions and so on, and now you are putting some plasticizers in between and you are spacing them out, as he pointed out, and as a consequence they can move more freely with respect to one another, and that would essentially mean to say that there would be a decrease in TG, right, because it's very easy to activate movement in these molecules. So plasticizers as a consequence, for instance phthalate plasticizers can be used for improving the flexibility, okay, the ability to deform a polymer, okay. And what is interesting is these plasticizers, fillers, additives, impurities, dyes, absolutely any secondary phase, okay, makes nucleation more possible. Why? So hint, this is an example of, yes, it's actually an example of heterogeneous nucleation. It's a little bit like this, you want to nucleate sugar in concentrated sugar solution. Now you could introduce a sugar crystal. If you don't have a sugar crystal, introduce some other crystal, and it will grow around that particular crystal, and slowly you will actually get a sugar crystal. So it's actually an example of heterogeneous nucleation, alright. Now there is a very interesting theory associated with this. It's called the theory of nucleation, and you can show that from the theory of nucleation that there is a critical radius below which this polymer might actually form this crystalline region, but it will again dissolve away. It will form this crystalline region, but it will dissolve away. But if the crystalline region that is actually formed, this nucleation that is happening, if it happens beyond a critical size, then it stays. Below a critical size, it dissolves away, okay. So as a consequence, this is interesting because it is actually capable of crystallizing, and because each of these secondary phases are capable of creating crystalline regions, a good question to ask is, can I control the average size of the crystallite in polymers? The answer is absolutely yes. You can control the size, the average crystallite size in a polymer. Will that influence mechanical properties? Absolutely. It will totally influence the mechanical properties, right? So very interesting. Now I will stop at this. To summarize, we looked at crystallinity as something that can be controlled using processes, okay. So, and we noticed that when it comes to crystallinity, it does have an impact on density, not surprising, because in fact densitometry is used to determine the degree of crystallinity after all. And then strength, no question about it, because the direction of crystallinity basically determines the direction in which the strength is maximum, and this correlates with the degree of anisotropy that's there in the modulus of the material, alright. And then I asked you a question which I think is rather interesting, can you play with the colors, composition being the same? The answer is yes, you can play with crystallinity, that means you can play with process. But you can certainly play with the composition also. For instance, you can introduce dyes and pigments. Can you make optical filters? The answer is yes. Thickness, you can use the idea of destructive interference, for instance, to make optical filters. And can you generate polarized light and a Polaroid? The answer is absolutely yes. And then we also looked at crystallization, and we realized that crystallization depends upon secondary impurities, secondary phases that exist in the system, the number of crystallites, and hence the degree of crystallinity also is determined by secondary phases that are there in the polymer. What else did we learn? Can you have any arbitrary critical radius for nucleation? No, it is fixed. Below that critical radius it just dissolves away. Okay. So these are the things, and as far as pedagogy is concerned, we discussed the Socratic method, the Socratic circle, and by and large it is a constructivist approach wherein you ask leading questions so that students build knowledge. For instance, I think students did not know about this when they entered the class, but they knew a little bit about this, but then we built on already existing knowledge through leading questions, and they came up with this, and they were also able to envision how a process could be modified to achieve, let us say, certain optical lenses that could be filtering, maybe even high resolution filters or anti-reflecting, correct, and also useful for making a Polaroid, for instance. So with that we conclude. So the lesson as far as pedagogy is concerned is Socratic method can be used to construct information and pad information on top of one another in a manner such that students see correlation between ideas that are communicated, concepts that are communicated in a particular field. Thank you very much. So I will see you again in the next SWAYAM session.